This is question 10 from the 2012 PAT. So in this question, we were asked to plot a graph with a bunch of properties, including it being continuous. Now the terms continuous and differentiable are terms you'll probably hear quite a lot when it comes to graph sketching. So in this video, I'd like to give you a visual intuition of what they mean, and what they actually look like when you plot a graph. But first, what is a continuous function? Well, if I was going to sum it up in one word, it would be joined. And if I was going to sum it up with a description, it would be, you should be able to draw this function without your pen ever having to leave the paper. So for instance here, I've just randomly chosen to plot x squared, which is a continuous function for all of x, because I can draw all the way down here and up there without having to lift my pen up off the paper. So what types of functions aren't continuous? Well, there's three main types: functions with a vertical asymptote, functions with holes in them, and functions with a jump in them. Okay, so firstly, what does a vertical asymptote look like? Well, here I've plotted the function f of x is 1 over x minus 1, and you can see that in this function, for the value of x equals to 1, there'll be a division by 0, so the function is not going to be defined at that region. And as you can see here, from this side it blows up to positive infinity, and this side it blows up to negative infinity. So if you're going to draw the function from this side, at this point here you'd have to take your pen off the paper to carry on drawing from up here again. So next, what is a hole? Well, if you look at this function here, g of x equals x squared minus 1 over x minus 1, you can see that in this numerator, we could factorize it using the difference of two squares to be x plus 1, x minus 1. And then if we had that, that'd be x plus 1, x minus 1 all over x minus 1. So we could cancel out the x minus 1. So this is really exactly the same as the function g of x equals x plus 1. And if you see that here, we've plotted the exact same graph. However, there is one very subtle difference between the two graphs. In the case of this actual function here, at the value of x equal to 1, the numerator will be 1 minus 1, which is 0, and the denominator will be 1 minus 1, which is 0. So the function will be equal to 0 over 0, which is not defined, which means just at the point of x equals 1, there's what we call a hole in the graph, because the function isn't defined. Now we won't be able to see it using this graphing software because we can zoom in indefinitely, but theoretically, if I put an arbitrary limit around x equals 1, what would happen is if you zoomed in far enough on x equals 1, as I'm doing here, you'd get to a point where there's just a break in the curve because it's not defined at just that point. And obviously, at this point in the graph, you'd have to take your pen off the paper in order to carry on. And finally, what does a jump look like in the graph? Well, it looks just like this here. You can see there's a jump between the two lines. So this function here, we've decided that for x is less than 0, the function is going to be x squared plus 2 here, and for x is bigger than 0, we've let our function be x squared plus 1. So you can see at x equals 0, it jumps down to this graph here. So next, what is a differentiable function? So once again, I've plotted x squared because it happens to be a differentiable function. So a differentiable function, if I was going to sum it up in two words, would be smoothly joined. And if I was going to sum it up with a phrase, you'd have to be able to draw the graph not only with just keeping your pen on the paper, but also without your pen having to make some weird, sharp nudge at some point. But officially, differentiable just means that the function has a well-defined derivative, or in other words, it has a well-defined gradient at whatever point. So what functions aren't differentiable? Well, there's three main types. The first one are graphs that are discontinuous, the second ones are graphs with cusps, and the third ones are graphs with vertical tangents. So firstly, graphs which are discontinuous. So it's worth mentioning that if a graph is differentiable everywhere, that implies that it will be continuous everywhere. Because if we have a look at some of the graphs that we looked at before, for instance this one here with a vertical asymptote at x equals 1, you can see that at this point here, it's very unclear what the gradient would be, because if you come in from the left, it looks like it could have a gradient of negative infinity essentially at this point, and if you come in from the right, it looks like it could have a gradient of positive infinity. So at x equals 1, what the gradient is unclear. So secondly, what is a graph with a cusp in it? Well, here we have the graph, the modulus of x minus 1, which just means that we get the positive value of x minus 1. And you can see that at x equals 1, there's this sharp point in the graph, and that's what we call a cusp. And it makes sense that this wouldn't be differentiable because coming down from the left here, it seems that the gradient would be minus 1, and coming up from this side on the right here, it seems that the gradient would be plus 1, but at exactly this point, it's very unclear what the gradient would be. And finally, what's a graph with a vertical tangent? Well, it looks just like this over here. So you can see that once again, at x equals 1, in this graph, there's no vertical asymptote, but for this small region, the gradient does seem to become infinite which means that the gradient isn't defined, which means that once again our function is not differentiable. So as one last example, this function here with the cusp in it will be continuous because you can draw it completely without taking your pen off the paper, but it's not differentiable because the gradient at this point is unclear. So most graphs you come across at your level will be both continuous and differentiable, but it's worth knowing what those terms mean for the rare cases where they're not.